And one of those examples would be to look at the way many people think of images, which is as two-dimensional arrays of pixels, and then to consider other representations, such as your representation of mapping from R2 to colors represented some way. We could do RGB, for instance. And also another representation might be vector graphics, which I think is quite superior already to two-dimensional arrays of pixels, but perhaps not as good as.
I got a little sound effect. So what was the second idea?
Oh, just vector graphics.
Oh, vector graphics. Yeah.
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 I think it's superior.
Vector graphics. Yeah. Vector graphics as a representation.
Yeah, I guess.
Yeah.
No, I guess what I'm thinking of is you have some primitive building blocks like geometric shapes and Bezier curves and that kind of thing, and graphics constructed that way. And I think that's already superior to thinking of things as two-dimensional arrays of pixels, but perhaps not quite as good as total functions from R2 to colors. Yeah.
Yeah. Yeah, because it's a tiny fraction of what you can express in the general model.
Yes, that's true. Yeah. But that's a good criterion.
Yeah, there's some interesting things you could look at if you go in that direction. The collection of geometric stuff. One thing is like if you want to do spatial transformation, that's a pretty common thing to want to do with graphics. And so if you have like I say a square, right? And it's represented by this thing that says I'm a square and here are my corners, something like that, or here are my angle and width and things like that. And then you want to apply some spatial transformation to it. How do you do it? And what does it mean to do it correctly? And and so what graphics programmer, the way they've been conditioned to think is you transform the vertices.
That's right. And that's the way I would do it if I was working with some data structure which specified squares as say corners or sides or whatever. Yeah, that's true.
Yeah. So then it raises the question: is that correct? And that question raises another question: what does it mean to be correct? And that's the important question. And if you just assume that somehow, like you just, I just decide that's what it means, right? That's normally what people would do. I just decide that's what it means. So what are you saying when you decide that's what it means? Do you want this decision to be consistent with anything at all else? Do you want anything to be true about it? Is this choice? Is there something that you think is true if you make this choice, and false if you make some other choice? Like why not just reverse the vertices, or eliminate them, or multiply them or something like that? Why not all those choices instead?
Oh, you mean as in order to implement rotation?
Yeah, exactly. Yeah. Why don't you just return the empty image?
I see what you're saying. Okay. And so you're then led to the question of what's my underlying model for a square? And that might lead you in a fruitful direction.
Yeah.
And then eventually.
Yeah. And then do that with every single choice you make in programming. So every time I'm about to make a choice, it's like, so why do I want this choice? Is there something true about it? Can I just make arbitrary choices about every single thing? Or no, only the choices that somehow leave me like feeling comfortable. Choices that leave me feeling uncomfortable I shouldn't make. I think that's probably a big criterion for most programmers, whether they know it or not. Yeah, and then why not take some completely ludicrous alternative and do that instead? What's better about your alternative?
Yeah.
Can you pull anything out of this subjectivity and make it objective?
Okay. So
you can't. You're not doing anything like science.
Okay. Let me push back for a little bit and say that one could make the argument that geometry in, say, two-dimensional real plane is fairly well understood in a mathematical sense, and that there are textbooks out there that talk about what's necessary to do to rotate
Okay.
and project or translate it or scale
All right.
it.
Okay. So if people who wrote those textbooks are going to write your program for you, then that's somewhat a compelling argument, maybe a little bit. But you're the one who's going to write the program, and you're justifying it by saying somebody else understands something. So how do you know that what you write is compatible with what they understand?
Well, I would hope that there would be some theorems around why the rotation, let's call it algorithm, is correct.
Uh-huh.
Yeah.
Yeah. Now, there could be, and those theorems would have something even more important than themselves, which is what it means to be correct.
Right.
Right. If there's some theorem that says this is correct, right? Then there must be some notion of what correct means. Yeah. And we haven't even so far said anything that's suggestive whether some mathematician's idea of what it would mean to be correct is the same as what we're thinking. You know what I mean? Like they said, do this and it's correct. And I say, okay, I'll do that, it's correct. But it turns out that his notion of correctness and mine are completely unrelated to each other. And I've got this kind of false reassurance. So it's really important for me to understand, what does he mean by correct? And do I want that to be what I mean by correct? And what if I take sources from two different, if I take theorems from two different sources and they have two different notions of correctness, and I use both of them, I can't possibly be right? Because they disagree with each other and I agree with both of them. So I'm not even agreeing with myself at this point.
Oh, absolutely. I agree with that statement.
Yeah.
Take it from two sources, but maybe you don't take it from two sources.
Yeah.
So are you gradually leading to suggesting that representing images as functions has this correctness criterion?
Well, first of all, I don't represent using functions. Those are the denotations, not the representations.
I'd better be precise with my words.
Yeah, if I conceptualize imagery as functions, then it's easy for me without pointing to anybody else for authority. It's easy for me to completely explain what I mean by every single operation in my library.
Yeah.
Right? So I picked a model, and in that, and then I have a library. It's a bunch of vocabulary, and now I can define everything in my library simply and precisely in terms of that model. So it's not like me picking it makes something true. It's like it makes it easy for me to say something that is true.
Yeah.
And then we look at it and say is it at all related to my intuition about imagery, and have a kind of a useful relationship to my intuition about imagery also. If it was it's a completely unrelated thing, it's like pairs of socks or something, or it's just completely, or it's a sound or something like that, we would just say, okay, that's self-consistent, but it really is not what I was looking for in an image library. Right. So it should have something to do with my intuition or my vague intent around images. And it should be completely well-defined and self-consistent. And what it means has to be simple. And the reason for that is that I'm not very smart. That's the reason for that. Neither are any of my friends, Yeah. So the simplicity is so we know what we're talking about. The machine checked or socially checked is what keeps me honest, or helps me not make mistakes without noticing.
Yeah. I guess what I'm struggling with is that, okay, your denotation is functions.
Yeah, that's mine, but that's not the only possible one. Yeah.
Right. Yes.
Yeah. I'm not at all trying to argue for it. I'm saying pick any at all one, like when we're talking about, yeah. And then say what it means to do spatial transformations, and rotation is one of them. And if you do your thing, what you had in mind for squares, it's right. It'll turn out to be right, and you can prove it. But if you start trying some other spatial transformations, after a while, you'll find that it's wrong.
Okay.
So the first one you tried, you got lucky in a sense, but also you hang out with programmers, and that's one of the few that they actually use because it happens to be correct for how they want to implement it.
Yeah.
But once you try some other things, you'll find out that implementation choice is actually wrong.
Okay. And can you give me an example of one of the ones that's wrong?
Yeah, absolutely. If you take a warp a non-linear kind of a bend or a twist or something like that.
Yep.
Yeah, and you do that by saying so you define how you're going to map space. So a rotation is a function from space to space. To every point to something around the origin and that kind of thing. So a warp or a twist or something like that is if you take a square and you apply that transformation, you won't get a square. Right? You won't get a polygon even because all the interior points, right? If you map them through space, they're no longer going to be.
I get it now.
Yeah, yeah.
No, I get it now because I don't have the vocabulary within that particular, I'm going to call it denotation, to actually draw the square. I just don't have it. And it's probably those weird curved sides it's going to have probably aren't Bezier curves either.
Yeah, they're not.
Right?
Yeah.
So
or the first one we tried would be Bezier, and so would the second, but the third one we tried would be not Bezier.
Yeah. Well, I'm just suggesting that if I'm only limited to Bezier curves, then there are some warps that will exist which won't map to Bezier curves, and then I can literally not draw this thing.
Yeah, or but what would be more likely to happen is that you would draw it, and it would be wrong. But you'd be content because you'd say, well, that's what I defined it to mean. I'd like, look, that's the definition. There it is. But you only get away with that because you only get away with that when you don't ask your implementation to be true of anything. Or you don't ask anything to be true.
That's funny because I think if it was actually me programming it, that's the point where I'd get discontented with the denotation that I'd chosen.
Oh, good. Okay, I would hope so. Yeah.
Where I'd say, no, that actually doesn't apply to my understanding of geometry on the real plane. And then I'd be like, oh, maybe I should just use the real plane or something like that.
Yeah, totally.
Something like that.
Yeah, I think that sounds like a pretty plausible evolution of one's thinking.
Yeah, I just feel like at the point where the square wasn't drawn properly, sorry, the warped square wasn't drawn properly, that's where I'd go, but that's not correct. And then I would realize that in fact I do reason about things with more machinery than the denotation I'm actually using. Be like, actually, this really wasn't everything. I thought it was everything, but there are other things I use to reason about geometry, and therefore this is limited and can't possibly be correct, and I'm going to have to change my denotation at this point. That was a really great example, Conal, because I did not see it until you mentioned what happens to the sides of the squares in the warp. Yeah. Okay, that's really cool.
Isn't that funny? Isn't that funny? Yeah. And like graphics people, people who do graphics programming, they're so used to using matrices to represent their spatial transformations that they don't realize that they can represent almost no spatial transformations. And all the ones that they happen to be able to represent, they wouldn't notice this fundamental bug.
Yeah.
Right? It works for everything they can represent. But that's not because spatial transformations in general and polygons like each other. It's because they picked such an incredibly impoverished notion of spatial transformation.
Yeah, that's really interesting. So let me ask you a question. So back where we were talking about, say you choose sort of vector graphics representation as your denotation, I then said, well, I could consult mathematical textbooks to see if it was correct or not, and they would have theorems and so on. What was it about that process that seemed wrong to you? Was it this understanding that actually it wouldn't work for things like warps?
No, it wasn't that. It was it was the way I interpreted what you said, which it might have been not the way you meant it. I interpreted what you said as like there are some experts over there who have done a lot of thinking about these kind of things, and then it's kind of done, and I get reassurance. And I don't need to worry about it anymore. That kind of just knowing that that's out there addresses my.
I see.
That was how I interpreted what you said.
Right. That wouldn't be very good. No, I guess I did mean actually going and studying the mathematical textbooks and then hopefully trying to formally verify some theorems in the library, and that might then have led to understanding that it was deficient.
Yeah, it might have. Yeah, it's kind of luck of the draw. It depends on the text you use and whether how general a notion of spatial transformation they're interested in. And if it's computer graphics, then mostly they're going to assume that there's nothing outside of their favorite representation they should be interested in, whereas almost everything is outside of it. So in other words, that they'll have like affine, or they'll have affine and projective kind of things. Yeah. But then there's also another. I mean, this doesn't have to. You don't have to abandon vector graphics at this point. There's another choice, and sometimes it's exact. Sometimes it's really the right choice. No, darn it, I want my vector graphics, but I want a nice story, and I want to really understand vector graphics. So the technique or the implementation choice to transform a shape. I transform the vertices used to define that shape, right? So that's the thing that people do. The transform of the shape is the shape of the transform. In a way, it's a little homomorphism thing, and that equation, that property is true for some transformations and some shapes, and it's false for. So instead of abandoning the whole enterprise, you can just say, okay, I want to model my, I want to understand my transformations as functions on space, but I'm not going to allow all transformations. I'm just going to allow some of them. Yeah, and so I can have like a restricted subset, and there's some property, and hopefully it's a mathematical property, like linearity, something like that, or affineness, or productivity, or something like that. It's some kind of mathematical property, and then now you have that property, and now you can go back to your question. I want to transform the shape by transforming its control points and so on, and the kind of the geometric, that key information, and then you have to ask yourself the question: is that correct or not? And it completely depends. I mean, you really have to consider every shape that you're wanting to make and every kind of transformation you're wanting to make, and then try to prove that theorem. Yeah.
Okay.
And you will never do that unless you think about the specification. If you just think, I'm just going to implement stuff, I'm a programmer, right? Then this question will never arise, and so you'll get some random hodgepodge of correct and incorrect.
Yep.
Yeah. Or another possibility is you'll get something right, but it's only because you never push the edges, right? So in other words, like I'm just going to stay in my little safe zone over here with like linear transformations and a few little primitives, stuff like that. But if you do that, you're kind of safe, but maybe you missed a whole lot of interesting stuff you could have done.
That's right. Yeah.
Yeah. So if I know what the specification is, I know what the correctness theorems are, then I can really go as far as I can while staying within correctness.
Yeah. But the more I think about this particular example, the more I realize that while you were implementing it, if you had a keen eye, you would notice that there might be deficiencies. Like, say you've done a non-linear or non-affine or transformation, you've moved the vertices around. That's perfect. You've done that correctly. But now you're drawing straight lines between these vertices and saying, well, that's what the square looks like. That's at the point where you go, okay, that can't possibly be right.
I hope so.
My whole notion of line is, or that a square that's been transformed will have straight edges is bullshit.
Yeah, it is.
Yeah. And that's where you might start thinking more deeply about what you're doing. Yeah.
Absolutely. Yeah. And there are classes of spatial transformations that have certain properties. Like there's some that are length distance preserving. You take two points, you spin them through, you get two other points. Are they the same distance apart from each other or not? There's a name for that, isometric or something like that. Right. And then there are ones that preserve angles or don't preserve angles.
Right. Okay. So I'll bring us back to our original topic, which was that I guess I was trying to show a specific example of denotational design to maybe illuminate what the whole thing's about. And I thought maybe I'd look at this example of images, and that when one gets stuck using two-dimensional arrays of pixels, when one thinks of an image as being that, you're hopelessly hampered, really, on what you can do with those images. you know, like if you want to zoom in,
Uh-huh.
for instance, everyone already knows you can't do that. This is simply not enough information there to do so. You'll just get bigger blocks. So you get blocks of pixels representing what was a pixel before. And
Yeah. So,
it's
and
pretty tricky too.
yeah, I mean, if you've been shackled to a computer for long enough, you'll no longer see that as wrong. You'll come to see it as right.
Yes,
I mean, that's what that's what every computer I've ever used has done.
that's right. Yeah.
Yeah. So there's some other perspective. Like there's this some perspective that is independent of the computer and programs and
Yeah.
that sort of behavior we're used to getting. Yeah, there's something else, and that other thing is what informs you to say, I don't really like this blockiness. Right? If you didn't have that, you would go, blockiness. Of course, that's always what happens when you zoom in. As if that was your whole universe. You wouldn't even think anything was wrong about it. So I think it's that there's the kind of things that the weird artifacts, what I think of as anomalies that we experience, when we use software that hasn't been designed well, or just like you said, the data isn't there, right? And like, what can I do? One artifact or another, yeah. And then there's this other thing that kind of says, that's not quite right. And it's that other thing I think that we want to pay attention to and make it precise. And that's the denotation for me. That's where that goes.